look at it. So because everything works out exactly the same, except it will be there will be an h there, x there to worry about. But if you just careful, there is really seriously no serious change. So instead of a equal 1, how about I put an x there? So, or what changes? So I put x here, x, square root of x. So far so good. Now I do the same trick. I still multiply by the conjugate, so it will be square root of x, x. Okay, so every one is replaced with x. So now I still have the trick works again. So I have a square root of the difference times the sum, which turns everything into a square. So it will be x over here and x over there, and x over here and here too, square root of x. Okay. Okay. So and then what's left? I still you can see that x now, instead of 1 canceling 1, we're canceling x in the numerator, right? And then in the next line we're still canceling h. So that's the good news. It works out every time. Okay, so and then I'm left with something fairly simple. What's the answer? So that expression on the right, so be careful. So now we have two variables at the same time, but it's really not a variable. X is not a variable. I mean, a variable x is the variable of the function, but we are still doing implicitly one point at a time. So x, think of x as fixed, just like that 1 was fixed. Now x is fixed. So, but h is what varies. So, and the limit, and to understand which one which one matters, just look at the limit. H matters. X is fixed, so the limit is with respect to h. So h is going towards 0. So what do we get? In the denominator, yes. That's the answer. So the point being, well, actually, I think I got ahead of your question. Your question was about the difference quotient. So then initially, so then really it is technically applies only to this part. This is the difference quotient in an arbitrary point x. So it is an expression with two variables: the original variable of the function x, and then h, which is the increment of our how far we go away from that point x elsewhere. Okay, so but it is really looks like there are two variables, but it is if we're careful in our computations, remember the spreadsheet h is fixed. Why? Because if we're doing spreadsheet computation or any kind of computations, then we cannot have limits. It has to be a specific number. So h, I typically pick h equal 0.1 or something like that. Yeah.
Would there ever be like a graph or a function graph, and it will say find the difference quotient of this? Like, how do we find?
Yeah, you could. It definitely could. Yeah.
I mean, figure out what h
the difference. They will ask you to find the difference quotient probably for different values of x. So, and then if you plot them, you could. Well, I mean, they have to supply at least the value of h.
They have to.
Yeah. Yeah. So h is sometimes, incidentally, sometimes the this is a different notation for h. Delta x, which stands for the difference of x. Okay, so we'll talk about this notation later, but this is so far that's what it means. If you encounter a problem like that, I don't think on this test, on this homework. So as you can see, even the h is the variable, but it does not. Once we get to actual derivative, as you can see, it is h goes to 0 and stays there. So at the end, h disappears. So no h here, right? And then x is actually variable. So h is just a a tool or like intermediate variable to be disposed of and then to be forgotten in order to evaluate the limit. The limit is with respect to h. Okay, so of course, okay, so that's the computation. That's pretty much what we care about as far as the finding the derivative as a function is concerned. This is the computation. So yesterday was computation of the derivative at one point, okay, that was 1. Okay, now I take that computation and just make it more complicated, but really, if you did the computation with the number correctly, then you shouldn't have any trouble with x's. It's just more cumbersome. You have to be more careful, but the algebraic tricks that you use still apply. And you can see that you still have every step we went through, including identifying this as a indeterminate expression. All of that will happen. Whatever you canceled with the specific number will still cancel. And in the end, well, now what is actually what matters now, the big deal about in calculus is that you have a new function. That's at the bottom is a new function of the same variable. Okay, even though the input of the variable is the same, even though the output might be different in the sense that think about it, if x is time and the original function f is location, right? So the derivative is what? F location x time f prime of x is what? Look at the, in any doubt, limits are kind of stand in the way, and they seems to be some magic there, doing some magic, but look at the difference quotient. Location minus location in the numerator, and dividing by the segment, the interval of time, the length of the interval of time. So what is the meaning of that? It is the velocity, is average velocity, so that is the average velocity. The difference quotient itself is average velocity. And then that's the point of the limit, is to make it this average velocity into instantaneous velocity. And then most of the time you don't use the instantaneous anymore, just too long. So you just say it's the velocity. So average velocity is always over a period of time, over an interval, and this one is for an instant. So every x being time, you know exactly what the speed was, or velocity was like. So at x equal 1 it will be 1 half, and then at 3 it will be 1 over 2 squared of 3, and so on. So the exact value, you just plug in, and you have your function all mapped out. The difference, there's the other difference quotient. So not the other, but it's just this is the difference quotient that originally we used, but the slightly different expression is we use next, I believe, at some point. This one. So once again, this is we just looked at the difference quotient, and this is the other one, which is just as good, but subject to confusion, because they don't look similar. You just remember that this is the same thing. It's just a different. You do it in a different way. So either you are looking at A. In either case, here A is this was still when we were talking about fixed A, fixed location. So we still were doing the derivative 1 point at a time, and that's to emphasize that A is not variable but fixed. That's why we use A instead of X. So X and H are variable, and X and A is not. Okay, so as far as limit is concerned, that's certainly the case. But if we wanted to be more, if we want to do more of the function simultaneously rather than 1 point at a time, we could. We just saw it. Then yeah, we have to do it this way. Which one of these two better is not? Either one is good enough. The second one is slightly better, conceptually, because that is harder to forget that this is the difference quotient. That is change of y over change of x. and this is here I'm using the second formula. In the next example, can you see x squared minus 1 squared or x minus 1? And the answer is 1 because it was still evaluated at a particular point, but you can imagine what happens is I would, well, the choice of variable is unfortunate, and that's why it's not easy to fix, but since we're talking about this, let me carry this out quickly. So suppose I'll take the I guess this is how you can make it slightly more sense of it. The confusion between x, the variable, and x, also the variable, just in a different place, is here, just facing us. In that sense, there is less confusion with the first definition, because x is not present. So let me do that. So let me do this function again, f prime, what we did last time, but f prime for 1 over x, but at the same time, everything at the same time. Okay, so so f of x is 1 over x. The difference quotient, let me at x. What is difference quotient at x? At a variable point. And the answer is, this is the second version would be, how about this f of x, t minus f of x, t minus x. How about that? Okay, so you recognize once again this change of y over change of x. Okay, so our x is what this one is. This x is fixed, and t is variable. It is variable in the sense of our limit. But before you get there, go through algebra. And then it should fall into your lap the answer. Okay, so you should probably, let me do it without using LIM as I did here. Let me just go with the difference quotient and simplify. Okay, so the function is 1 over x, and as the question was, I will replace x with, well, I don't have to do anything with x, it is already x, right? The second one, denominator t minus x, the only real work needs to be done is with the first expression, but look at it, all I have to do is just replace x with t. So this version of the difference quotient takes less work to set up. So what do I get? The first term? 1 over t, okay, and then just in case, recognize if t goes to x or even x goes to t, you're gonna get 0 over 0, so that's not good. We already know what to do. We do common denominators, so it will be, in the numerator, it will be x minus t over tx divided by t minus x, right? Remember what we did last time to simplify. Right.
T times x.
Yeah, so these two are the same up to a sign. Okay, so I end up with negative 1 over tx. Okay, and then remember this is the definition. In my difference quotient, what happens is we're making our time increment go to 0. Time increment being simply the denominator. So t minus x goes to 0, or, which is the same thing, t goes towards x. And so what do? I substitute, right? So, I mean, not like this, but rather I'll put arrow here. So t goes to x, and so what's the answer? Negative 1 over x squared, yes. Comment that it has to accompany the whole thing for as long as x cannot be equal to 0, which we, not only because we don't want to divide by 0, but also because because the original function was undefined as well, and the function is discontinuous, you cannot do substitution anyway. Or x not equal to 0 because 1 over x, or 1 over x squared, what is it? Well, let's say 1 over t is continuous for t not equal to 0. So once again, why the substitution works? Because the function involved is continuous. Okay, and we stay away from the 0. So that's the answer. So the comparing, the big deal is comparing the function with its derivative. Well, let me write what's the conclusion. Conclusion, f of x is 1 over x. Well, a good term. F prime of x is negative 1 over x squared. Okay, so we will go back and forth a lot in the sense that the computations like this will appear a little bit early on. The analysis, actually, what it provides us with is either whichever is we are interested in the function itself or in its derivative. So either the function we know well, and then it will tell us something about the derivative, or vice versa. We know the derivative, and from the derivative we can figure out something about the behavior of the function. Okay? Especially the latter is more important because, well, it's primarily, remember, this is still slopes. These are still slopes. But infinitely many slopes taken at the same time. Yesterday we did one slope at a time, and we didn't even assemble some function from those slopes, remember? So which is pretty much what if you go backwards. But if you don't assemble a whole function from it, at least you know that, look at the slopes. So what can you say about the slopes? Look at them. Algebraically, what does it tell you? What can you say about negative 1 over x squared?
It's always going to be negative.
It's always negative, yeah. Always negative, so slope is always negative. All slopes are negative. So the function kind of will look like this. Well, it's not exactly like that because, but roughly speaking, it will always be going down. If it is going anywhere, it's going down. Truly, it's not. It doesn't look like this because there is a hole in the domain, and so the actual function looks more like this. And then there are two branches, and one branch is not located where the other one is. So the conclusion will be to derive information about the original function from this simple observation. The derivative is negative, so the proper term about the function, what does it tell you? If you remember the term, f is decreasing. Remember what it means? Decreasing function. Yeah, that's right. As x grows, you will be always going down like this. So every pair of points that you pick, it will be going down. We have to be careful here. It will be decreasing on negative infinity 0 as well as 0 plus infinity. Okay, so there are two different branches, and they are behaving in a similar fashion. So like I said, this is pretty much the whole thing about decreasing functions, is that if you pick any 2 points within the domain, within these intervals, the one to the left will be always higher than the one to the right. Okay, so x progressing left-right, what happens to y is going down. So that's the whole thing about decreasing function. With the increasing function, it's the opposite, right? So why do we do this? Well, considering that we can plot the function very easily. This is what the function looks like, 1 over x. 1 over x. Y equal 1 over x look like this. Of course, it is decreasing, and you can plot it. Why do we care? Because if we are to develop any kind of theory that involves absolute or infinite accuracy, then we have to consider the possibility that we zoom in on one of those points over here, and then maybe it behaves like in some nasty way, maybe, we don't know. Okay, so now we do know that it's not the case, because slopes are all negative, so you cannot get anything like that. So every time you plot, there is also a possibility that if you zoom in, it will look very different, but the derivative tells you for sure that what's happening there. So once again, the point of being is infinite accuracy that we can acquire, even though the information is certainly not infinitely accurate as far as the value of the function. It's still a question, but we know where it goes. So that's what derivative tells you. The kind of qualitative behavior of the function goes up, down, or maybe it's not going anywhere.
What would negative 1 over x squared look like?
Okay, let's plot it. It looks kind of similar. So as you can see, it's positive, right? But the function itself is not increasing. The function is first increasing, then decreasing. So the derivative itself, it's virtually impossible to guess what the derivative is going to look like from just looking at the function itself, because ultimately you do it one point at a time. So you pick a point here, and then you zoom in on this location over here, and then what it gives you, not here, it gives you a single point on the graph. So it's here somewhere. So small circle of our no matter how small, but a little circle, a little piece of the graph of the original function. We zoom in, we recognize that. So that's what on the right is not going to happen. What's really going to happen, that there's a straight line there, as what we did yesterday, remember? So we're going to see something like this. Zoom in, right? Zoom in, there's a straight line there, and then we look at the slope, and we plot that slope on the new xy plane. And that's how one point at a time we create the whole derivative. But like I said, if either we are thinking graphically or numerically, just as I described, that's one thing, that we are actually interested in the derivative, and we're looking at the graph of the function and original and get to understand the derivative. If we can compute, as the example what was about, it's the opposite. We found the derivative exactly, and then it has simplified situation dramatically. All we have to do to understand the function, original function, is just look at the sign. The sign of the derivative tells you a lot about the original function. So up, down, or none. And one problem is, of course, what happens if the behavior changes from decreasing to increasing. What's so special about this point?
It's 0.
The derivative will be 0. Yes, that's how I'll find it. But the importance is that is a minimum. Well, decreasing, then increasing. Okay, so any kind of optimization problems will involve the derivative. Okay, so we'll get to that later. But what we were supposed to discuss before that is the theoretical issue of when the function has the derivative. It is possible, not just like we have discontinuous functions, we have functions that are not differentiable. The word for finding, so differentiation is the word for finding the derivative. Then differentiable is the function that has the derivative, and non-differentiable is then the one without. This is still one point at a time. One point at a time, so their function might be otherwise all good, but at one point it's not. Just like after all, the derivative is a limit, so limits might not exist, right? So just like with the derivative, the continuity is defined through a limit, and whenever that limit does not exist, the function misbehaves at that point. So once again, the standard example of this function is the sine. Okay, sine of x. Okay, so there's a gap in the graph of the function, so it's discontinuous to begin with. What about differentiability?
It probably has an average.
What?
An average slope.
No, the limit of the slope, not the average slope. Well, I mean, unless you mean the average, the slope of the secant line, the slope of a secant line like this. So suppose we are naturally interested in the value of 0. So this is one of the secant lines. This is one of the secant lines. These are the 2 points. We pick a point of our interest. Let me mark it red here. So this is the questionable point. The point of questionable behavior of our function. So I draw a straight line through it and another point on the graph of the function that gives me what we call a secant line, and then I look at the slope of that secant line and see whatever happens whenever we are making that gap, this gap, smaller and smaller. So where's my h? This is my h. This is my h. This is my denominator of my difference quotient, while this will be the numerator. Well, no, that's not the numerator. Where is my numerator? No, it is my numerator, right? So denominator, and this is the numerator of the difference quotient. Okay, so just try to imagine what happens to these secant lines as h gets smaller and smaller. What's happening?
The secant line goes closer and closer to 0. They're flat.
No, they're not going to be flatter. The h is the other point. The other point will remain. This other point will remain on the graph. So one point is the red point in the middle. This point. Okay. The other point is the blue point. It remains on the graph. And I mean, it remains on the graph, but it's moving. Okay. So what's happening? So that point is moving this way. That point at the top is moving this way. What's happening to the slope?
It's getting sharper.
It's getting sharper. So slopes are getting sharper. Okay, and so how much sharper? So my red point, well, the answer is there is no limit to it. I could have it as sharp as I like. So I start with this, and then the next one might look like this, right? So if h is really small, the sharpness of, as you describe it, is increasing, and so you can see what's happening is counterclockwise rotation of the secant lines. And what is at the end of this process, if you can see?
Be a vertical line.
Yeah, at the end of the last one is the end is a vertical line. And what's the slope of the vertical line? Undefined, infinity, doesn't matter. The point is that the limit, our limit doesn't exist. So our difference quotient, which is the slope of the secant lines, so this is difference slopes are difference quotient. So the limit of the difference quotient does not exist. So the function is not differentiable at 0. So f is not differentiable at 0. It is differentiable everywhere else. If you look at if you step away from the graph of from 0, then there is nothing going on. So either you have this, or you have that. So there are only two branches left, and whichever point you pick, you cannot pick the endpoints, right? So any point you pick on the graph, what's the slope? Slope is 0. So the function is fine elsewhere. So the function is differentiable. It's a 0, 0 whole. So that's the derivative. It's undefined at 0. The original function is defined at 0, right? In spite of its continuity. The derivative will look like this. It will be 0 everywhere, except there's a gap in the domain at 0. Okay, so that's the differentiability versus non-differentiability, but this was a little bit cheating. Example wasn't perfect because the function is discontinuous to begin with. So if we try to think in terms of motion, then what we have here is we have teleportation. Look at that teleportation. What's the speed of teleportation?
Instantaneous.
No, the time is instantaneous and the distance is not 0, so it's infinite. So the speed is, it doesn't matter how short your teleportation is, because it is instant, it is infinite. The speed is infinite. Okay, so that's pretty much what we have discovered here. Okay, but it's also possible that even though there is no teleportation, we're moving gradually. However, the change of direction is instantaneous. And then we, once again, have no differentiability. The example is standard. And that's the absolute value. First thing to remember is, of course, that this function is continuous. Okay? So there is no problem with it in that respect. But it's not differentiable at 0. You can imagine, just think about motion once again. Suppose it's a motion. Representing motion. X is time, y is location. Y location. So can you describe this motion?
Slowing down and speeding up.
No, there is no. That's a location. We're not talking about the velocity. So if to the left of 0, so the 0 is some moment something happens. Before that, we're moving. Which way we're moving? You remember, y. The location is on y. The x is not location. X is time. So the motion now is one-dimensional motion. This is our road.
So we're moving backwards?
We're moving backwards, yes. We're moving backwards on this, this is my motion, like this. Like this. What's the speed? 1. And then what now? Let's separately consider what's happening to the right. So this is the other one. After t equals 1, what happens? After t equals 0, x equals 0, what happens?
Turn around and start moving forward?
Yeah, and once again the speed is once again 1, but the direction has changed to the exact opposite. So try to execute that. Hypothetically, can you move? I can't even imagine how you can do it with a car, but even a person would be impossible to instantly change direction to the opposite. Not gradually, but instantly. Because no matter how close you are not slowing down. You compare to x squared. The graph of x squared, it looks like this. So y equals x squared. What's the difference? It's very similar, but yeah.
Your slope's slowing down.
Yeah. So your speed towards the origin slowing down, and then once you turn around, you are speeding up gradually. Okay. So that's why it is from the point of view of motion, the behavior is reasonable, and it's parabola. That's how the object thrown in the air behaves. It goes up fast, maybe slows down, then kind of for an instant stops up there, then starts to accelerate down. Okay, so that's fine. Instant change of direction indicates that is not something that we can describe.
You can do that with like a roller coaster?
roller coaster? What exactly do you want to?
I guess it'd have to hit a spring or something, but I guess it'd slow down.
Yeah, the spring that we can do it the next similar problem. Yeah, there is that it has to contract, and that even short moment creates non-instant change of direction. Okay, so that is short moment of time. It is not like don't want to try to idealize something that is not ideal. If we are trying to develop a theory, we want to say motion. Then we want to throw out things that describe things inappropriately. So that's what's on the left. You don't want to describe motion in this manner because, well, it is just not realistic to change direction instantly. This is what it is when it is okay. So this is bad, and this is good as far as the derivative is concerned. And now, how do we guess the which one's good, which one's bad? We can see it, right? Without any computation and extra analysis. What's the difference between the two?
Instantaneous versus gradual.
Right. Yeah, that is if you interpret it as motion, but it is just an interpretation. We go there whenever we kind of not sure what's going on, and we want to verify that common sense applied to this abstract mathematics. But if you just look at the two curves, the orange curves one and the other, what's the difference?
One of them curves,
Well, I would kind of disagree. What?
Just
It curves. The first one does curve. It just curves really, really, really badly. Okay, so a straight line doesn't curve. This one, there is actual curving, and it curves in a really, really bad way. Okay, so another way to see it's
the slope is the same throughout on the left one, whereas on the right one it changes.
yeah. No, well, I mean, you could still you can. Here's a bad example of another bad function looking like this, really bad. It is changing. The slopes are changing, except they're not changing in the right way. You still have to change the direction instantly. So no, the corner is the problem. The corner is the problem. That's how you identify. You tell two functions apart. I mean, differentiable and non-differentiable function apart is the corners. Either corners or gap. The extreme case of a corner is actual gap. A gap that is definitely function is not continuous. Then it is motion or anything else is derivative cannot possibly exist. But if the function is continuous, then you look for corners or cusps. So that. Something like that. Once again, the function. Remember how we define, not define, but rather understand graphically a tangent line. We zoom in. Imagine zooming in. If I zoom in on this one versus that one, so what do I get?
the quadratic is eventually going to be zero. The slope will eventually be close to zero.
So if I zoom in, if my circle is really, really small, I'm going to get this, right? What about the first one?
It's going to be an 8.
It will still the V. So that's the problem. It kind of sounds strange that you keep zooming in and the picture doesn't change, right? It was V originally, remains V. And the second one is actually curved, becomes straight. It seems that the former might be better, but actually the whole calculus is based on that idea that the picture is not, how should I put it, does not, on the different scales it looks differently. Okay, when it looks the same on different scales, we cannot handle it with calculus. You may have you heard of fractals? Fractals? That they have that one of those things that the characteristic of a fractal is that it is you zoom in and it looks the same, or at least it doesn't change into anything easy, such as easy as a straight line. As an example, well, trees, for example, Well, trees and the, you can see the trees at the tree, look at the tree at the base, and it has, several branches, okay? You zoom in on one of the branches, it has more branches. And you keep zooming in, and there will be more and more branches. Roughly, that's what we're talking about. Or a shoreline. So you look at from the space, it looks curvy and very, very rugged. You zoom in, you look at it from an airplane, it's still rugged. You look at from standing there, it is rugged, and you try to use microscope, it will still look rugged. And that's exactly what we cannot handle with calculus. In fact, from personal experience, sometimes if you sleep on a plane, okay, and you wake up and you look outside and you're not sure, and then you look green clumps, and then what is it, a big forest or just little clumps of trees, or maybe it's grass, we already landed, okay, so you don't know what it is. But calculus is simple. What we're handling is shapes that when zoomed in becomes straight. Okay, so that's the thing. That's the good news. Good news is that straight becoming straight is a good news, because then we know what to do with them. They're ultimately, we very much from pre-calculus remember straight lines are easy to handle. Right, so that we understand what their slopes are, intersections and directions, and it is really very easy to handle. Later on, you deal with planes as well, but for the time being, it's entirely about straight lines. Okay, so so it can be demonstrated, and let me, if not to demonstrate it, but I think I may make a case, is that it is a theorem. Every differentiable function is continuous. In other words, well, the example that the example was the opposite, but not the opposite. It's called the contrapositive. Have you heard this word? It's the same statement, they just with negative, in the negative sense. So if I say that every differentiable function is continuous, then what I can say is that if a function is not continuous, then what? Then it's not differentiable. It's the same statement. So that a logical mistake may be made a lot of times. Then say every differential function is continuous, then maybe if a function is not differentiable, then it's not continuous. Look at the direction. So the direction was differentiable means continuous. And then the order is, once we negated both of them, it goes the other way. It goes from continuous to differentiable. Okay? So, well, it's better. You certainly can think of probably examples in logic of contrapositive statements, but in mathematics that's especially common. It's just one of those logical mistakes that are so common that it just sounds quite ridiculous most of the time. So the example shows that this example shows that it shows the differentiable function, and then we showed also that it's also not differentiable. Okay, but it certainly doesn't prove what we. One example doesn't prove the theorem, so you have to actually demonstrate that the function that is not. So if the limit doesn't exist, of f of x goes to a, does not exist, then limit f of x minus f of a, x minus a, does not exist either. Okay, so it takes some time to see, but actually, as you can see, the second second limit is somewhat more complicated. Okay, so we're not going to do that, but once again, remember that there are more continuous functions. We remember we threw out functions that are not continuous because they describe most of the continuous processes poorly, such as motion or any kind of continuous change. So that's why we don't want to stay away from them as much as possible. But then there are fewer. Even then, the example now, the importance of this example is that they're a function, even though they are continuous, they're not differentiable. So this is how commonly it is illustrated. This idea is like this. So if I have all my functions like this, then there are fewer, not all functions are continuous. So suppose these are continuous. And what is I could actually put an example here. Look at this example of my sine function outside of the continuous function. It's a function, but it's not a continuous function. Okay, so I put it as an example there to indicate that why is it there is actual gap between the function and the continuous function. So there is something out there. There are a bunch of discontinuous functions. Okay, so these are discontinuous. But then there is also they are differentiable. These are differentiable. Okay, so and then once again, as an example, I'll put here like this the absolute value. As you can see, that V shape, the absolute value function lies inside of the continuous circle, but outside the differentiable circle. Okay, so there is to indicate that there is a difference. Yeah.
Are you saying like there's more continuous functions?
Yeah.
than
Yeah.
differential?
Yeah. At least there's at least one more, right? At least one function that is differentiable, continuous but not differentiable. We already have one example. That's the absolute value. But you can think of a number of other examples. As long as there are teeth or any kind of corners, cusps, the functions becomes not differentiable instantly, and so you can produce many examples of functions that are continuous but not differentiable. So continuity is the absence of a gap. A gap certainly is like this. That's a gap, maybe a big gap or some wild behavior also. But differentiability is not only they have to be together, but they also you cannot have sudden change of direction. Okay, so there is one example, however, which kind of at least the might be outside of that explanation that I gave you. A graph that looks like this. So suppose this is my function, and the graph looks like this. Okay, no corners. But it's still not a differentiable function. Why? You see why not? What's so special about this point?
The slope stops increasing and then starts decreasing.
Yes, well, yeah, but what is the value of the slope at that particular point right here? If you can, what? It is undefined or infinite. Yeah, so that's the problem. The derivative cannot be equal to infinity because infinity is not a number. So which means that it's not differentiable. So still not differentiable. In fact, there is a very simple example of such a function. It is the cubic root. Cubic root actually looks exactly like that. So this is, well, let me make the full plot. Actually, probably matters. Let me plot x cubed first. X cubed looks like this. Okay, xy. And then if I take the inverse, you can see what's so special about this point. What's so special about this point? What's the slope? 0. Now, if you take the inverse, you have to flip x and y. So what happens to the 0 slope? Well, 0 slope means horizontal, right? If you flip, horizontal becomes vertical. So vertical, I have my shape. It's exactly the same graph, but it will look like this. Okay, and so the slope becomes it's the same point, and slope is infinite. Slope is infinite because the tangent line is vertical. So there is really nothing wrong with the vertical tangent line, but its slope is infinite, and so as a function, it's not differentiable at that point. Okay, so that's the exception from that rule that you have to look for corners. It is possible to have simply infinite slope, even though as you can see, the function is really nicely looking. It's in the inverse of x cubed, very smooth and nice. The other word for differentiable is, by the way, smooth. Smooth, that's not smooth. Any kind of roughness, that's weird. That's not smooth. So in kind of man-made affairs, the non-differentiability is in fact common. So you might remember that discussion of the tax, that tax rate changes abruptly, but if you adjust the definition of the taxable income, the actual tax bill is changing continuously. Remember this? So the slopes of this do change abruptly, however, which means that it's not differentiable. So once again, this is income, and this is tax bill. So not the rate, that is changing abruptly. What is changing abruptly is, in fact, its derivative. Okay, so this is tax bill, and as you can see, this is as far as the taxpayers are concerned, it's the behavior is okay because it is continuous, changing. So your income, if your income is changing continuously, your tax bill will also be changing continuously. Okay, but if I want tax rate, remember what it is. So it starts with 0 up to this point, then it becomes 10%, and then become 20%. Okay, they are aligned, but I put them on two different xy planes because they're the y-axis is not related. So tax rate, tax bill, not the same units. So I keep them apart. Okay, so remember this discussion, except the way we did it, went this way. We started with the tax rate, which we know that it changes abruptly from as you change, you leave the bracket, and in the next bracket the tax rate suddenly is higher, but really the way it is done is the actual tax bill is changing continuously. But now, what if we go backwards? What is that we're looking at? What is the relation between these two functions?
The tax rate is
Yeah. It is the derivative. No, it's the derivative, yeah. The derivative, with the exception of those points where the corners. So the tax rate, remember the derivative is the rate of change. So that's the rate of change of your income. Your tax is in fact the tax rate. Okay, so that's exactly what you have, and that doesn't have to be motion, but because it's man-made, we end up with a function, though continuous, it's not differentiable, right? So it has two locations, two change of brackets where there is sudden change of direction. So it's suddenly speeds up. If your income grows, your tax bill suddenly starts to grow faster. Okay, so it is, you feel the difference. You feel the difference. There's something, that something has happened. Even though there is no abrupt change in the amount you pay, the rate changes, and it changes suddenly. So ideally, if you want to really fix it, you make a curve that is smooth like one of those. Okay, so okay, so we have been talking about the derivative as a function. We computed it once or twice. We did it, this is, you can do this point by point or otherwise, because it's made of straight lines, so every straight line has single value of the slope, and that's why the derivative will be a single value. So where else did we see the derivative as a function? So, well, derivative of the function the function on the left will be, well, what's the derivative of the function on the left, the absolute value? Slope to the left of 1, what's the slope? Negative 1. To the right? 1. Okay, so what's the function? Negative 1, 1. It's the sine function, except it's undefined at 0, but otherwise it is pretty much the sine function, negative 1 and 1. For the x squared, we already know the answer. It will be a linear function. Not only when your speed is constant, when your speed is accelerating linearly, then your position is changing quadratically, and vice versa. That's why we're moving along parabolas. So parabola is quadratic function, and let me do it one more time. So it is important for any kind of physics. So your velocity, well, you can start from before, so acceleration is constant, negative g, okay? And then your velocity is linear. So it will be, say, negative gt as an example. So your velocity, if you just keep it like this, starting with a velocity 0 and then you release it, it will start to decelerate, and so the value of the velocity will be more and more and more negative. Okay, so it's a linear function. So you start with the derivative, which looks like negative g, like this, negative g. Okay, then you plot the velocity, okay, so which will look like this. Okay, so negative gt. And thirdly is we have the location, which is quadratic, which will be negative gt squared over 2. Okay, roughly. So that's the physics. If you're not sure about this, you can always just go through differentiation. So if I start with my location, so going backwards, we're not really prepared yet to go forward from acceleration to velocity location. We're interested in differentiation for now. So we're starting with location, which is negative gt squared over 2, and we start differentiating. So if we want to find the velocity, what do? We do the difference quotient. Okay, so it will be negative, so h goes to 0. We have negative g. Okay, I'm using t as a variable. That's not wise. Let me put x here. X, so time is x. Okay, so gx squared over 2 minus, so that is my numerator. Hold on, I have to do x plus h here. Okay, so I substitute x plus h, so I have my g of x plus h squared over 2. So I take my function and replace x with x plus h. Okay, and minus negative g x squared over 2. Okay. So as you can see, I want to carry out this information without specifying what g is, because it doesn't matter. In different units it will give different number, but the differentiation works out just as well. Okay? Okay, so what happens next? What happens next? I have to do something with the numerator.
You know that h is going to 0, so that you can say, you can
then I have 0 over 0 again, right? That every time you try to plug in h equals 0, you will have an indeterminate expression 0 over 0. So what's the answer? The standard answer. Indeterminate expression, how do we handle it? We forget about the limit for a moment and do what? Algebra. Algebra, in this particular case, all we have to do is expand. We expand that square over there. I can probably simplify it slightly, so what is it? Let me simplify it first. So I'll have 2h in the denominator, and I'll have negative gx plus h. And let me factor g out as well, so that we would have to carry it around all this time. So I'll take g out. 2 is also out, common denominators, and what I'm left with is negative x plus h plus x squared. Okay? Right, g is factored out, 2 is factored out. I have a very simple expression in the numerator. Now I do actual algebra. I expand in order to get rid of what? X squared kind of in the way, because that's what makes it all 0. I need to cancel h, so I have g here, and here I have negative x squared minus 2xh minus h squared plus x squared over 2h. Okay? Just expand, you know, the distributive property, if you like. That's what I'm doing here. Now x squared cancels every single time. Okay, I'm left with g negative 2xh minus h squared over 2h. I cancel h, which is what we were after anyway. So I divide the numerator by h as well as denominator by h. Okay, and then I'm left with g negative 2x minus h over 2. Okay, this time the function now is continuous. There is no h in the denominator, so once it's out, we can substitute. Substitute, and what do I get? H is gone. H is 0 this time.
Negative 2xg
Over 2. So negative gx, as predicted. So indeed, this is a uniformly this is the velocity, and this is how it's changing with time. So it will be growing or rather decreasing at the rate of g per second. Okay, so that's how it happens computationally. We did it numerically as well. Graphically, there was a picture. Let me just quickly find that picture of us making graph. No, that's not the whole function. That was what was the name of it? A graph from pieces, probably. Well, that's not it. Well, no, that's not it. That's not it. Hold on a second. The one that we did, yes, slopes. Okay, so I guess let me. This is what we did last time, but this is just one at a time. So we could actually let me try it. I have a few minutes left. Let me do it from scratch anyway. So that's computationally, algebraically rather, how we do it. Graphically, I might have. Oh yeah, here it is. Okay, so I have my graph of my function might look like this. Doesn't matter. Okay, that's my function. I pick a few. I break the graph into several pieces, and I will be looking for tangent lines at different locations. So just a few. And the slope of the graph at each of these locations will give me the value of the function. So that's y equal f of x. And then now I will collect information over here, which is corresponding to each of these axes. So I will try to translate, kind of bring it down, my function, onto the x-axis again, but what I will be collecting information about will be slopes. Okay, so this is how I could start doing it. Here's there's a straight line here possibility. Well, let's make it green, not green, straight line here. Okay, so there we go. This is the information that I collect from the very first location. That's not the way the derivative is going to look like. That is just information about, we're going to get the information from this, which is the slope. But then I have to do it several times. This one, no, that's not it. Again, straight line. I want straight line. No, that's not close enough. Okay, another one. And then one more. So I'm not trying to connect them into anything because that's not helping. Because we're not gonna, doesn't give us anything. It's all very approximate, but it's good enough. Okay, so this is the information that I have collected. Now I look at these and identify slopes. So, I don't know, 1/2 it appears, the next one -1, -1, 0, 3, 0, 1, roughly, I'm doing roughly 1 and I don't know, 1/2. Okay, that looks reasonable. So these are the slopes of these lines, and these are the values of f prime of x. At those values of x, these are the x's that we care about. Okay, so for each of these x's, I'll have now this value plotted. Okay, so let me do that. Let me try do copying. There's no copy. Okay. So we don't need anything else. These numbers are the only one that we care about at this time. We just paste it here. Okay, so what I'm going to be doing here, I will delete what we don't need anymore. So I'm going to delete this. I delete the graph, not this one. I delete the graph. Okay, in fact, these are also now of no consequence at all. These were the values of the original function. All I care about is the values of x. Okay, now I'm taking these values of x and plot those values of the derivative of the slopes. Okay, so say, let me pick this color. Okay, so let's go with blue. Okay, so I need the axes. So say 1 and 2. Okay, so let's plot. So 1/2. So this is the first one, 1/2. Okay, the next one is -1, so it's here somewhere. -1 again, 0, 3 here somewhere, 0, 1, 1, and 1/2. Okay. So as you can see, it's a lot of work, because we do it one point at a time. There's really no way around it. With algebra, we do it just everything simultaneously, but it's still pretty hard. So at this point, I can just connect it to some curve that might seem reasonable, and then say, well, that's my derivative. Maybe. Okay, so that's the derivative. If you scroll back, there's really no. Can you guess the new function from old? Probably not. So it is done one at a time. All right, so we'll just continue next time. Yeah, okay.